Dr. R. Sugurat Samuel is working as professor in physics in SRM University, Chennai. He is also training students for IIT JEE, AIEEE, and BITSAT. He has more than 16 years of academic experience both in teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals. It is prescribed book in the syllabus for BSc Electronic Science by University of Madras. He has attended and presented papers in several national and international conferences and conducted many training programs and workshops. He has experience in both regular classroom teaching and also online teaching. His research areas are ultrasonics, polymers, crystal growth, and photovoltaic systems.
Welcome to UGC lecture series on Applied Sciences Electronics. We have been discussing about the concepts related to digital electronics. In particular, we are now in the concept related to circuits working based on the input waveforms. In the last lecture, we have learnt how the waveforms are generated. We learnt the concepts under the titles integrator and differentiator. We have learnt elaborately how the integrator and differentiator could alter the input waveform for a digital purpose. Especially we make use of the square wave for digital circuits. In this lecture, in continuation to that, we will dwell upon the concepts related to digital electronic circuits which work on the digital pulses. Here what we mean by digital pulses, the square waves. So, before we start today's lecture, let us see the session outline for this lecture. In this session, we are going to see the waveform generators again and a concept called duty cycle, and also digital circuits that work on waves and clock pulses. So, we are going to restrict ourselves with the concepts of waveforms and how these waveforms enable the digital circuits to function. Actually, in the last lecture itself, we have seen the importance of digital wave pulse. We have seen the concepts at length, and to test how much we have understood about the functioning of the integrator and differentiator, let us once again go through the two slides we have seen in the last lecture. Maybe an integrator and differentiator combined together, how they would produce waveforms. So, let us quickly have a recap of that and then move on to the concepts related to the typical waveforms. So, let us have a look at the slide and try to answer the questions. In the way itself, we learned lot of things. I think this diagram is quite familiar to us now. It is an integrator connected and a differentiator connected in series to the integrator, and here we have a waveform generator. It produces the square wave, it is depicted in the diagram, and we would like to know what are the waveforms available or possible at these two terminals after the integrator and after the differentiator. What is the output of an integrator when it is given a square wave? So, if we know the answer, here we can give the correct waveform, and similarly the output of the integrator is given to this differentiator circuit, and this output we can represent here. We can make a wild guess in the beginning itself. The integrator and differentiator are the complementary operations. In mathematics also, the integration function and the differentiation function, no, these two are the just doing the opposite in mathematics. The equations or the concepts, whatever we take, they are just the complementary operations. the one more reverse of the integration is differentiation, like that we can explain that also, that is a mathematical touch to the integration and differentiation concept. But as far as the waveforms are concerned, one thing we can immediately guess, the integration operation is nullified by the differentiation operation. So, here also with this basic knowledge about the integrator and differentiator, we can quickly make a guess for the output of the typical combinational circuit. Let us have a look at the slide. See, here we give the input as a square wave. So, in the intermediate there is one waveform generated and the output should also be the input, because the intermediate is once again made into the input, because the differentiator circuit will do the complementary operation of the integrator, or in other words the opposite of the integration operation. So, the output of the combination is very easy for us to guess. So, here we will expect a square wave again, but what is this wave? What is the output of the integrator when it is given an input of square wave? We need to recall what we have learnt in the previous lecture. So, let us have a look at the slide and know what are the waveforms possible in the cathode ray oscilloscope, which traces the waves. Let us have a look at the slide. See, these are the outputs. After the integration, the square wave is converted into triangular wave. Now, the triangular wave is fed to the differentiator circuit, that indeed produces a square wave. So, if we compare, the input is again obtained as the output after the integration and differentiation operation done simultaneously. Now, we have learnt the importance of square wave. How do we analyze a square wave? Is there any factor that we have to analyze in a square wave? Because we just learnt the voltage levels are just varying between the two values, the higher and lower value, and we have eliminated the time involved in the transition between the higher to lower or lower to higher level. We have not given much importance to the transition part. So, the stable part only was taken into account when we learnt about the square wave. Now, we will learn it elaborately based on the waveform itself. The duration of the stable state in the higher and lower state need not be same. Only for the square wave, a perfect square wave, the higher level and the lower level should have the same duration. But in general, when we take any pulse and all, it is a modified square wave. So, the width of the stable state either in the higher or lower state will be different. So, let us try to introduce a quantity that would take care of the change in the duration. That quantity is called duty cycle. For any waveform analysis, this terminology or this term duty cycle is a very important term. Let us define what is a duty cycle. It is a very simple definition, it is expressed in percentage. So, let us define what is a duty cycle. A duty cycle is the percentage of one period in which the signal is active. A period in the time it takes for the signal to complete an on and off cycle. As a formula, a duty cycle may be expressed as this form: D is equal to T divided by P into 100. What are the terms T and P represent here? So, we need to look at the typical waveform, then only we will get the full understanding of the duty cycle. So, let us have a look at the typical waveform. So, here it is depicted. A duty cycle D is defined as the ratio between the pulse duration, which is represented as capital T, and the period of the rectangular waveform. Actually, here we restrict ourselves to only the rectangular wave. So, we have taken that diagram to explain what is a duty cycle. When we have the P in the denominator, which is represented, which is mentioned here as the period. What is a period? One time period. In regular oscillation and oscillation, it is the time taken for one crest and one trough, that is typically for any sinusoidal wave. Here also in the same light we can understand what is one time period. Here the time period is the time taken for one higher level and one lower level of the waveform. So, the time period could easily be recognized or identified in the wave represented as a picture here. So, let us go back to the picture again. See here, this is the period, it includes one higher level and one lower level duration. So, this is typically the period, and for what duration the pulse is at the maximum level or higher level, that is represented as t. So, definitely when we have a look at this diagram, the t will always be less than p, t is always less than p. So, this t divided by p is a fraction which is less than 1. So, when it is multiplied with 100, we will get the duty cycle in percentage. If the waveform suppose stays in the higher level throughout, then the t will be equal to p. In that case, that ratio will become 1, the percentage is 100. So, duty cycle will have the value 100. If suppose the waveform is not varying, it is totally in the lower state throughout, then the duration t will be 0. So, in that case the duty cycle is 0 because there is no variation at all. So, duty cycle helps us to have an idea of what is the width of the higher stable state in the entire period. It is expressed in percentage. So, we can take up this technical quantity for analysis of waveforms. And here also in another way it is defined, duty cycle is the duty ratio. It is the time during which the pulse is in the on state, which is in the higher state, divided by the total, the on and off state. So, this is also defined as the duty cycle, and it is not multiplied with 100 here. So, the value will be in fraction, it will be less than 1 for any typical waveform. So, what is the use of this duty cycle? It helps us to analyze the waveform. We can also have a look at clipping that tells us how the percentage of the waveform, the duty cycle is varying. Let us have a look at the clipping. It is self explanatory. As the d value increases in percentage and now it is decreasing in percentage, the waveforms are varying between the lower to the higher. See, now the waveform, the d is increasing, so the shift is in the to the higher level. Now the duty cycle is decreasing, so the shift is to the lower level. So, we can have any value between 0 and 100 as far as a waveform which is a digital waveform is concerned. Now, we can look at the importance of duty cycle. A clock signal is produced by a clock generator. Although more complex arrangements are used, the most common clock signal is in the form of a square wave with a 50% duty cycle, usually with a fixed constant frequency. Now, we are moving on to a topic in which the digital circuits are going to be controlled by the pulses, digital pulses. So far we have concentrated on the square wave, we called that as a digital wave, in which the higher and lower stable state duration were almost equal. But now, after introducing the concept of duty cycle, we can vary the width of the higher level to a desired value. What is the use of it? What is the advantage of having a varied width? We will see the concept after a short break. Welcome back. We are discussing about the digital wave used in the form of a pulse. So, towards the end of this lecture, we will come to know what is the meaning of a pulse. Now, we have introduced the concept of duty cycle at length. 50% duty cycle means it is a perfect square wave. Now, why this duty cycle is very importantly considered for the digital signals? When we represent the input wave, input signal or input data in the form of a wave, all the time it need not be the typical square wave. Based on the input data, the higher and lower levels will have varying durations. So, first of all, for that kind of varying duration of the input wave, we need to have different duty cycles. Second thing is, to make any circuit work, we will use this digital signal as a pulse to control the operations. So, that also we will learn right now. I would like to show you a typical clipping or a diagram in which how a digital pulse represents the zeros and ones. So, let us have a look at the diagram. So, here the pulse is fed to the input of any circuit. This is how the signal is varying. It is varying between the two stable states, higher and lower level, according to the data that is fed, according to the data that is given. So, here the direction is marked. So, this is how the data is fed. So, this 0 is fed first and then 1, then 0, then 1. So, that is why the direction is mentioned here. So, if you look at typically this waveform, they different portions do have different duty cycles. So, we can analyze the waveform with the concept called duty cycle. It is used, very much used. And second thing is, for controlling a circuit also, the digital pulses are used. For that also the duty cycle concept is very much used. So, right now we have got a look at the way in which the data is fed in the form of a waveform. Now, as an example, here is one case in which the OR gate is given the A and B inputs in this manner. Look at the way in which the inputs are fed. See here, up to this duration it is 0, and then for a short duration the value 1 is given, and then again for a short duration this 1 is given. And when we simultaneously have a look at the B input, the 1 or ones, the values ones are given at two different durations. It is not matching with the A, but what will be the output? The output is going to be 1 when A or B is going to be 1. So, this is how the output is obtained. So, what is the conclusion after having a look at a typical OR gate which produces a waveform for two different inputs given to the two terminals A and B, two inputs A and B. So, digital circuits can alter the duty cycle, that is the conclusion. Let us have a look at the slide again. Digital circuits could alter the duty cycle of a square wave. So, this is how it is altered. So, when we look at the A alone or B alone, they have different duty cycles, but here when we look at it, it is frequently varying. Here it is not that frequently varying as we have a look at the inputs, but the output is frequently varying. So, the frequency in which the variation taking place between the higher and lower value is high here. It is happening several times within a given duration. So, in conclusion, the digital circuits are actually altering the duty cycles, though they represent zeros and ones. In another perspective, when we say, when we want to mention that it is altering the duty cycles for the different inputs based on the logic gate or logical circuit that we have. Let us have a look at another example. So, here another example is given. Here an XOR gate, purposely for the two inputs A and B, the inputs are fed, they have a 50% duty cycle. This B is also having 50% duty cycle, but there is a small delay purposely made for the input given to the terminal B. What is the outcome of this? So, XOR gate will produce a higher value only when the input and output values are different. For the higher VA value and the lower VA value only the output is 1. Similarly, the lower value of VA and higher value of VB. It is I hope you remember the truth table for XOR gate. So, accordingly the output is produced. So, when we have a look at the output, the width is totally different. So, the duty cycle of the two inputs are totally altered when we consider the output here. So, the digital circuits could alter the duty cycle according to the logical operation. Let us have a look at another example. This is called the delayed input. This is also one technique by which also we can generate digital pulses. Already I have mentioned a digital pulse is the one which has a desired duty cycle, maybe a very small duration. For a very small duration the value will be high, remaining time it will be very low. So, the duty cycle will be very less compared to a square wave. So, how these pulses could be generated using digital circuit. So, let us have a look at this. So, here it is an ordinary AND gate. We know the AND gate will produce an output only when the two inputs are high. So, here there is an input given and there is a delayed input given for the other terminal of the two input AND gate, and here we have several NOT gates. They are represented in this manner. Why do we have several NOT gates? Can't we have only one NOT gate? What is the title? It is a delayed input. So, we want to delay the input that is given to the second terminal here. So, because of that the input given to the second terminal is delayed by this much time. Here the x axis represents the time duration. So, accordingly it is delayed by a small value, and as an output only when the two inputs are high the output will be high. It is happening only for a small duration here. So, it has produced a pulse. Delayed input devices could also produce digital pulses. We can alter the duty cycle using the digital circuits. Similarly, one more example let us see. Have a look at this diagram. This is a NOR gate. Here also same mechanism is used, 3 times it is inverted. So, definitely this is an input, inverted input. Twice if it is inverted, then this will also be the maximum when this is maximum, but here it is inverted definitely because it is a odd number of inversions happening. So, look at this mechanism. Here the output will be high only when the two inputs are low as far as a NOR operation is concerned. So, at this end of the pulse, at the end where the value changes from high to low, it is called a trailing edge. This is called rising edge and this is called trailing edge. So, the pulse is generated in the trailing edge region. The same explanation holds good for this delayed input device. The delayed input devices could be used for producing digital pulses. Slowly we are migrating towards the concept called pulse. We started off this lecture with the concept of square wave, duty cycle and all that, but now we are slowly changing our focus towards the concept called pulse. So, we need to know the importance of pulse. Pulse has a very small duty cycle, that means it has got the higher stable state for a very small duration. In precise equipments and all or digital circuits and all, the duration in which the state is high is very small, even it could be in nanoseconds, microseconds, etc. So, in precise operations the pulse width is very important. So, let us know much more about the digital pulse. So, these are actually the pulse generators. This is also one example. This clearly indicates how a digital pulse could be produced. And here I would like to highlight another technique, that is called the propagation delay. Earlier we have purposely given a delayed input. When the input was given to the gate, it was purposely delayed by allowing the signal pass through several inverters and all that. But here there is a concept called propagation delay takes place. The gate or the circuit in general would also have an internal delay because of the functioning of the circuit. After all, it is the movement of electron and all that, though it is happening at a very high rate, there is a time delay involved in all the operations. So, that itself will produce a delay, that delay is called propagation delay. So, let us see what is the propagation delay. Look at this typical diagram in which the input is given here. This input is fed to the second input and the inverted value is given to the first input. So, that is why it is in bar, it is marked, and here the output itself is happening not at this expected region. In the previous diagram, in the expected region instantaneously we expected the output, but here in this the output is happening at a delayed rate. It's here, no, this is not matching with the output of the AND gate. But why there is a delay here happening? This delay is because of the operation that is happening in the AND gate itself. So, this diagram is also a self explanatory diagram which tells us the output of the circuits would also have a delay. So, instantaneous output we may not be able to expect in some of the circuits. When the circuit is very big, complicated, the propagation delay is naturally happening 1. So, this will also alter the duty cycle. So, accordingly we should design the circuits. Now, let us try to define what is a pulse. Before that, let us see what is synchronous circuit and asynchronous circuit. We could divide the digital circuits into two with these two names, synchronous and asynchronous circuits. In synchronous circuits, the inputs are pulses or levels and pulses with certain restrictions on pulse width and circuit propagation delay. Therefore, synchronous circuits can be divided into clocked sequential circuits and unclocked or pulsed sequential circuits. Synchronous circuits are triggered by an external clock. The clock here represents a pulse generator would produce digital pulses. So, that would control the synchronous circuits. Then what is asynchronous circuit? An asynchronous circuit is the one which does not employ the periodic clock signal to synchronize its internal changes of state. Therefore, the state changes occur in direct response to the signal changes on primary input lines, and different memory elements can change state at different times. Here the memory elements are the ones which store the data. So, let us have a quick look at the diagram which represents the synchronous and asynchronous circuits. So, this typically tells what do they mean. A synchronous circuit is the one which is controlled by the external clock which produces pulses, and in the case of asynchronous we do not have an external pulse, external clock to control it. So, I hope we have covered a wide range of digital circuits, started off with the concept of square wave and then moved on to the concept of duty cycle and then moved on to the concept of pulse. So, why the pulses are important? The pulses are important because many of the digital circuits are functioning on the pulsed signals which are called clocked signals to the digital circuits. So, now let us summarize today's lecture. In this session we have seen the waveform generators, the concept of duty cycle, the digital circuits that work on waves and clock pulses. Let us test our understanding by answering these questions. Define a duty cycle. What is the value of duty cycle for a perfect square wave? What are delayed inputs? What is meant by propagation delay, differentiate between synchronous and asynchronous circuits. So, with this I would like to conclude today's lecture. Thank you for